Hello all, as we continue our look at probability and a further deeper dive on probability tables, or sometimes called two-way tables, or also Karnow maps. A little change from the two-way tables that we did before is that two-way tables generally had, instead of a probability inside them, they had the number of elements in that set. So either one is a very useful tool, two-way table or probability tables, but just note that probability tables all have probabilities in them. So that means the key difference that can be quite helpful is that you know that the total probability of all events that's ever possible must always equal 1. You can never have a probability that adds up greater than 1 because that is greater than certain, which is technically impossible. So that is really handy in making a probability table versus a two-way table, is that you can put that 1 in straight away, and that might mean that helps you calculate certain values. A probability, when to use a probability table versus a Venn diagram, I almost always say use a probability table instead of a Venn diagram, just because they have a little bit clearer information, and they give you I've just forgotten the word. The complements. It gives you the complements, or the knots, so the dashed values, which are really handy instead of trying to. You can find them using a Venn diagram. You can do it using that. What are the numbers that are like? What's the probability of not B, for example? Well, then you have to go, okay, there's B, so then actually I need the numbers outside of it. So that's equal to 9 on total of 15. So you can do it, but a two-way table, probability table is going to naturally give you that, and more intuitively. So yeah, it's just like a two-way table, but it has probabilities in it. So let's straight away get into it. If A and B are events such that blah, 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 all of that, find probability of B dash, find these probabilities. So let's make a two-way table. Since we are given information about complements and we're asked to find information about complements, it is going to be much more intuitively simple to do that with a two-way table. There we go. Sorry, or a probability table. So let's call that A and not A, and that B and not B. And as I said before, the first thing you can do is always put the total is equal to 1. Okay. What is the probability? Probability of A is 0.6. So that's not probability of A by itself. That's not in here or in there. That is just the probability of A occurring is 0.6. The probability of B occurring is 0.5, which goes over there. There we go. And the probability of the intersect of not A and not B is 0.2. So not A and not B is 0.2. So we get that in there. So now we have that. We can calculate a whole heap of values because 0.6 plus something must be 1. So that has to be 0.4. 0.5 plus something must be 1. So that has to be 0.5. This value in here, so A intersect B dash, going across here needs to add up to 0.5, so that must be 0.3, which means that's 0.3, which means that's 0.2. And that works also reading down that way. 0.2 plus 0.2 is 4, 0.3 plus 0.3 is 0.6. So that works. So there's our two-way table, probability table, and now we can calculate the values as required. So what's the probability of B dash? Well, B dash, no other condition, so go all the way across, so that is equal to 0.5. What's the probability of A intersect B dash? So what's the probability of A and not B occurring? So I need A and I need B dash. So that meets me there, so that's my 0.3. Okay, probability of A union B dash. Okay, so we're asked for a union now. So a union you can't read directly off a two-way table or a probability table or a Venn diagram. But we do have the addition rule, which says the probability of A union B dash is equal to the probability of just A plus the probability of whatever just the second letter is, which was B dash, take away the intersection of those two things. So A intersect B dash. Okay. So probability of A we had is 0.6 plus the probability of B dash is 0.5. Take away the intersection of them, which is 0.3, which we had from the previous question, but again you could find it as A intersect B dash. So A, B dash, where do they cross over is the 0.3. So 0.6 plus 0.5 is 1.1, take away 0.3 is 0.8. So that's the probability of getting A or B dash. Let's do another one here. And I think that's it for this exercise. Yeah, so nice, short and sweet. From a group of people, 70% like drinking coffee, 24% like drinking tea, and 6% like drinking both coffee and tea. Now, if you haven't watched the previous video on the importance of these type of statements and the confusion between Common English and probability statements, I suggest going and watching the last 5 minutes of the previous video. But the key takeaway is that when it says something 70% like drinking coffee, there's no further elaboration or conditions on that. That's not saying the 70% like drinking just coffee and don't like tea. So yeah, just got to be really careful with that. So let's make a table like that, and we're going to go coffee, not coffee, tea, not tea. We know the probability needs to be equal to 1. And we could put these in as percentages, so it could be 100% instead, or we could do it as decimals. So we'll do percentages decimals, so total is 1. So 70% like drinking coffee. So that needs to be 0.7 there. And that's what I mean about, doesn't matter if they do like tea or don't like tea. We don't. Looking at this first statement, we don't know about these two boxes here, but we do know that's 70% like coffee, so it's a 0.7 down the bottom. 24% like tea, so same thing, that has to be 0.24 over there. And 6% like both, so whereas both is in here in the middle, so that needs to be 0.6. Now the rest of it we can fill in just by making everything add up. 0.24 needs to be 0.76. This needs to be 0. Oh, and that's a mistake. That's 0.06 for 6%. That needs to be 0.54. 0.54 to get up to 0.76 is 0.22. So that needs to be 0. That's not 54. It should be 6.4, which will make that 1.2, which makes that 0.18, which works both down and across. Cool, so that all works. There we go. So now we have that, we can answer these questions. Find the probability that a random selected person from the group does not like drinking coffee. So we want to find the probability that they don't like drinking coffee, which happens to be 0.3. Find the probability that a random selected person from the group does not like drinking coffee, but does like drinking tea. So we want to find the probability that they don't like drinking coffee, but they also have to do like drinking tea. Okay, so C dash intersect T. So C dash, coming down here, intersect T. There we go, 0.18. Done. Okay, and that's why probability tables are really handy. If you have any questions, as always, just ask in the comments below, Google Classroom, or shoot me an email. Thanks, and see ya.